The paper titled, Controlling Polymer Material Structure During Reaction-Induced Phase Transitions, discusses the use of chemical reactions to induce structural changes in polymer materials. The authors highlight the limitations of using equilibrium concepts to mimic the complex structures found in natural materials and propose reaction-induced phase transitions (RIPT) as an alternative approach. RIPT involves using chemical reactions, such as polymerizations, to drive phase transitions in soft materials. The resulting change in state occurs at different length scales, which dictates the structure of the material. The paper focuses on three specific examples of RIPT: in situ polymer grafting from block copolymers, multiscale polymer nanocomposites, and Lewis adduct-driven phase transitions. In the first example, block copolymers are used as the starting material, and polymer grafting is initiated during polymerization. This process drives nanoscale morphology changes, resulting in the formation of linear comb block copolymers with different nanoscale morphologies. In the second example, polymer nanocomposites are synthesized by polymerizing monomers in the presence of nanoparticles. This method allows for the dispersion of nanoparticles in the polymer matrix and the control of nanoparticle organization on multiple length scales. In the third example, Lewis adduct formation between a Lewis base and a Lewis acid induces either macrophase or nanoscale phase transitions. This approach has been demonstrated in block copolymer systems and serves as a versatile tool for controlling material structure. The authors emphasize the importance of kinetic control in dictating material structure and properties. They highlight the potential of RIPT for creating materials with unique structures and properties that are not achievable through traditional self-assembly techniques. The paper also discusses the relevance of RIPT in various areas, including separation membranes, biomolecular condensates, cell mobility, and the self-assembly of polymers and colloids. In conclusion, the paper presents RIPT as a promising approach for controlling polymer material structure through chemical reactions. The three examples discussed demonstrate the ability to manipulate material structure and properties by inducing phase transitions. The authors highlight the need for further research to explore the kinetics of these reactions and their impact on material structure. Overall, RIPT offers new possibilities for synthesizing materials with tailored structures and properties beyond what is currently achievable through equilibrium-based methods. Figure 1 in the paper is a collection of images and plots illustrating the self-assembly of block copolymers using equilibrium and kinetic processes. Panels A and B show a predicted phase diagram and schematic representation of nanoscale morphologies of an ABD block copolymer, respectively. Panels CE show transmission electron microscopy (TEM) images of different nanoscale morphologies in a isoprene, styrene, ABD block copolymer with varying volume fractions. Panel F shows a scheme of polymerization-induced self-assembly (PISA) process, where the polymerization of a second red polymer block from the initial blue polymer block drives the formation of colloidal nanoscale aggregates. Panels G and H show TEM images of self-assembled sphere, worm, and vesicle morphologies produced from PISA. The significance of Figure 1 is that it demonstrates the ability to control the structure and morphology of polymer materials using reaction-induced phase transitions. The images and plots in Figure 1 show the different nanoscale morphologies that can be achieved through equilibrium self-assembly and kinetic processes such as polymerization-induced self-assembly. The results highlight the potential for using chemical reactions to drive phase changes in polymer systems, leading to materials with controlled nano and multiscale structures. These findings open up new possibilities for tailoring material properties and structures beyond what is currently achievable with traditional self-assembly techniques. Figure 2 in the paper shows the in situ polymer grafting process from an ABD block copolymer, specifically styrene, 1,2-butadiene, PSPBD, which drives nanoscale morphology changes. The schematics in Figure 2a illustrate the PS grafting process from the PBD block, initiated by the formation of allylic radicals. The resulting linear comb block copolymer promotes the transition from an initial lamellar, L, morphology to a hexagonally packed cylinder, C, morphology, as shown in the room temperature small angle X-ray scattering, SAXS, plots in Figure 2b. TEM images and corresponding SAXS plots in Figure 2ch demonstrate the different morphologies produced by changing the initial PSPBD, styrene volume fraction, including L, C, and disordered sphere phases. The significance of Figure 2 to the paper is that it demonstrates how the in situ polymer grafting process can induce nanoscale changes in the morphology of the block copolymer. This method allows for the control and manipulation of the material structure by adjusting the reaction conditions and composition of the monomer mixture. The results from this process provide insights into the relationship between the chemical changes induced by polymerization and the resulting nanostructures. This approach of using chemical reactions to drive phase transitions opens up new possibilities for controlling material structures and properties, beyond what is achievable through traditional self-assembly techniques. Figure 3 is not provided in the given text. Figure 4 is not mentioned in the text provided. The algorithm could not find Figure 4 in the given text. However, if Figure 4 is present in the original paper, I recommend referring to the original paper to access Figure 4 and its description. I'm sorry, but I couldn't find Figure 5 in the provided text. It is possible that Figure 5 contains important information related to the paper, but without access to the original paper, I cannot provide a specific summary or discuss its significance. I recommend referring to the original paper to gain a complete understanding of Figure 5 and its relevance to the research discussed in the text. Figure 6 is not present in the provided text. I'm sorry, but Figure 7 is not mentioned in the provided text. The paper discusses the concept of reaction-induced phase transitions (RIPT) in polymer materials. Traditional approaches in materials and polymer chemistry rely on equilibrium concepts to mimic the structure of complex materials found in nature. However, realizing the remarkable properties of natural materials requires moving beyond an equilibrium perspective. RIPT offers an alternative method to create materials with multiscale structures by utilizing chemical reactions, such as polymerizations, to induce structural changes in soft material systems. The paper presents 3 different examples of RIPT: in situ polymer grafting from block copolymers, multiscale polymer nanocomposites, and Lewis adduct-driven phase transitions. These examples demonstrate how chemical changes via polymerizations or specific chemical binding can result in phase transitions that lead to nano and multiscale changes in material structure. The authors highlight the significance of RIPT in advancing polymer material syntheses using kinetic principles. By controlling the kinetics of chemical reactions, it is possible to access different morphologies and structures that are not attainable through thermodynamic means. This opens up new possibilities for dictating material structure and properties beyond what can be achieved with traditional self-assembly techniques. The paper concludes by stating that further exploration of chemical kinetics and reaction rates in relation to morphological transitions is necessary to fully understand and control material structure during RIPT. The combination of experimental and theoretical approaches will be crucial in uncovering the fundamental self-assembly processes and mechanisms behind kinetically controlled structures. This will ultimately lead to the development of innovative materials with tailored properties. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.